Right, let's get straight into this. Today, we are taking on the ultimate challenge, mastering the Cambridge Computer Science syllabus. And look, whether you're tackling the AS and A-Level 9618 or the IGCSE codes like 0417, 0478, 0983, 0984, or 2210, the strategy we're about to uncover is exactly the same. We aren't just going to sit here and review the textbook like everyone else. We're going to work smarter. We're going to find the analytical back door into every single question they throw at you. Our core focus for this explainer is one of the most notoriously misunderstood areas of the entire syllabus: Integrated Development Environment, or IDE features. Specifically, we're zooming in on coding and context-sensitive prompts. Now, I know what you're thinking. It sounds incredibly straightforward, right? You use an IDE every single day to write your code. You rely on dynamic syntax checking. You rely on autocomplete based on variable scope. It's second nature. But here's the crazy part. The official Cambridge Principal Examiner reports reveal a completely different story. Literally thousands of highly capable, smart students drop absolute sitter marks on these questions year after year. It's wild. So today, we're shifting our perspective entirely. We're going to explore the exact academic benchmarks, the underlying cognitive domains, and the procedural frameworks that Cambridge examiners use when they sit down with a red pen to grade your papers. By the time we finish this explainer, you're going to have the ultimate blueprint to deconstruct any complex algorithm or IDE question and extract every single available mark. You're going to be thinking like a hacker.
So, let's ask the million-dollar question. Why do capable students find evaluating algorithm efficiency and IDE features so incredibly hard? To understand this, let's imagine two hypothetical students. We'll call them Alex and Sam. Now, Alex is absolutely brilliant at memorization. Top of the class for recall. He overloads his exam answers with raw computer science facts. If an exam question asks about context-sensitive prompts, Alex writes this massive, sprawling paragraph listing literally every single feature of Visual Studio Code. But when the grades come back, he gets 0 marks for analysis. Why? Because he didn't actually answer the specific prompt. He just word-vomited facts. Then we have Sam. Now, Sam is a phenomenal coder. Probably builds apps on the weekend. But Sam always rushes during the exam. When Sam sees a question asking to evaluate an algorithm's efficiency, Sam just describes what the code does line by line, completely missing the requirements of the command word. Both Alex and Sam are incredibly capable students, yet both bleed massive marks on the final exam. The core issue? They completely fail to realize that the assessment framework prioritizes analytical depth over superficial breadth. Let me say that again. Analytical depth over superficial breadth. You cannot just list facts and expect an A-star. You must demonstrate a connected conceptual understanding that you can transfer to completely unfamiliar contexts.
And that fundamental misunderstanding brilliantly illustrates our core strategy today. The flawed approach, the one Alex and Sam use, relies on brute force memorization. It completely misses the edge cases, it ignores the specific command words, and it completely fails to analyze the actual context of the problem. It's basically hoping you hit the target by firing blindly. The hacker approach, however, that relies on logical, structured reasoning and a strict methodological breakdown. It's laser-focused. To execute this hacker approach, top-tier students use a very specific framework for their written answers. We call it the PEEL framework. P-E-E-L. That stands for point, evidence, explanation, and link. Let's actually apply this right now to a classic IDE context-sensitive prompt question. First up, your point. This is where you identify the feature, like dynamic syntax checking. Boom, 1 mark. Next, your evidence. This is where you reference the specific variable scope that's underlined in the actual code provided in the exam. You have to prove you read the snippet. Then comes your explanation. Here, you detail exactly how this feature catches faults pre-compilation, preventing runtime errors. Finally, your link. You connect your entire argument right back to the question's core objective, which is usually something about saving critical debugging time and reducing the development lifecycle. This PEEL structure proves to the examiner that you understand the why, not just the what. Make no mistake, applying this framework is the exact difference between an average grade and securing those top-tier marks.
Okay, before we continue and unlock the exact examiner secrets, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. It's the best way to ensure you're armed with the right strategies heading into exam season.
Now listen closely, because this next part is a massive revelation. When you dig into the Principal Examiner reports, they reveal a crucial, almost hidden secret. Students consistently lose marks by not showing they're working out. And here is the kicker. Even if your final code completely fails to compile, method marks can absolutely save your grade. This is what I call the method mark strategy, and it is honestly the ultimate backdoor into this exam. Think about it. When you are asked to write or evaluate an algorithm using IDE features, algorithmic thinking naturally requires step-by-step decomposition. The examiners actively want to see your analytical process on the page. They want to see your brain working. They want to see your exact data structure selection. If you write out a complex block of code and you accidentally forget a semicolon, or you make a minor syntax error in a loop, but your underlying logic and structure are mathematically sound, the examiner is going to reward you. Method marks literally prove that your analytical step-by-step process is actually more valuable to Cambridge than a perfectly compiling but unexplained final answer. It's like showing the blueprints of a house. Even if the paint job is wrong, the architect knows the house is solid. So, the golden rule? Never ever erase your working out. Keep those scribbles, keep those logic trees, keep those flowchart drafts. It is literal gold.
So how do we guarantee we get those method marks? We use an examiner-approved procedural framework to systematically deconstruct, solve, and evaluate any complex algorithm question. It's a 5-step system. Step 1. Deconstruct the given information. Strip away the fluff and find the core variables. Step 2. Break it into logical steps by determining exactly what data structures you need. Are we using an array, a linked list? Step 3. Solve systematically by applying relevant programming principles and executing your analysis with crystal clear notation. Step 4. Check for reasonableness. Do a dry run. Does the output actually make logical sense, or did your loop run infinitely? And finally, Step 5. Make justified recommendations. This final step is where that Peel framework we talked about earlier really shines, allowing you to present your findings with the correct, formal Cambridge terminology. If you follow the standardized 5-step sequence every single time you see a high-mark question, you are actively mapping your brain to the exact grading rubric the examiner holds in their hand. You are literally giving them exactly what they want to see in the exact order they want to see it.
Let's drill down into Step 1, algorithm deconstruction. What does that actually mean in practice? It means extracting the relevant data and actively selecting your analytical framework before you write a single line of code. Look, when you interact with an IDE prompt in the exam room, your adrenaline is pumping, but you need to stop and ask yourself, what specific problem is this context-sensitive prompt actually trying to solve? Is it helping the programmer identify undeclared variables? Is it auto-completing complex library functions to save time? By extracting this relevant data first, you completely prevent yourself from becoming like our student Alex, who just panics and writes down everything they know. Instead, you narrow your focus, you select the analytical framework, and only then do you proceed to implementation. It's like plotting your route on a map before you start driving. This active reading process doesn't just keep you on track, it massively saves you time and secures those high-level analysis marks that separate the A-stars from the Bs.
Okay, so once a problem is successfully deconstructed, how do we accurately evaluate its quality? This is where you have to put on your senior developer hat. You must look at time complexity. How long does this algorithm take to run as the input size grows from 10 items to 10 million items? You must identify space complexity. How much memory does it consume during execution? But listen to me carefully here. What really separates the top-tier candidates from the rest of the pack is their relentless focus on edge cases and the overall effect on system performance. And IDE's context-sensitive prompts can actually help a programmer identify potential edge cases during the coding phase itself, simply by highlighting unreachable code, flagging unused variables, or warning about type mismatches. If you can explain this exact relationship in your exam, if you can articulate how IDE features directly improve the evaluation of algorithm quality, you are operating at the highest cognitive domain Cambridge tests for. You are showing mastery, not just memory.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Right, let's get back into the hacker mindset. We need to look at the underlying architecture of the exam itself. This matrix maps specific IDE features directly to Cambridge's target cognitive domains. The first domain is knowledge and understanding. This is the absolute baseline. It's simply knowing that a context-sensitive prompt exists. The second domain is application. This is demonstrating how a developer actually uses a feature like autocomplete in real time to speed up their data structure selection. But the third and highest domain is analysis. This is where the big marks live. This is where you evaluate why real-time error diagnostics are absolutely vital for rigorous testing and efficient code implementation. Let's do a quick mental workshop. Imagine a flawed piece of code is sitting right in front of you. What PL paragraph would you write to explain how a context-sensitive prompt fixes it? Think about it. Your point would be identifying the error diagnostic feature. Your evidence is pointing out the red squiggly underline in the IDE indicating a variable scope failure. Your explanation is detailing how it catches syntax faults pre-compilation rather than crashing at runtime. And your link is concluding that this saves the development team critical debugging time and money. If you can map your answers across this matrix for every question, you are mathematically invincible on this paper.
We're moving into the final boss section of this explainer now. We are going to look at the top 3 mistakes. These are the exact pitfalls that principal examiners explicitly state they are tired of seeing year after year, paper after paper. Let's break them down so you never make them.
Mistake number 1, overflow and edge cases. Under exam pressure, students completely forget to check what happens when a variable exceeds its maximum memory allocation value, or they entirely ignore the extreme ends of data input. Let's say an IDE warns you about a potential integer overflow. If you don't explicitly mention this warning mechanism in your evaluation, you lose the mark. It's that simple. Mistake number 2, boundary conditions. This is similar to edge cases, but it's specifically about logic execution. This is where your loop runs one time too many or one time too few, usually because you used a less than sign instead of a less than or equal to sign. It's the classic off by one error. Rigorous testing, which is aided by IDE debugging tools like breakpoints and step execution, is meant to catch this. If you don't analyze boundary conditions in your written answer, your evaluation is viewed as incomplete by the examiner. And mistake number 3, honestly, this is the biggest one of all, missing specific context. Students love to give generic, rehearsed answers about IDEs that have absolutely nothing to do with the specific context given in the question prompt. If the exam question is about a specific bubble sort algorithm, your answer about IDE context-sensitive prompts must relate directly to the temporary variables and array structures of that exact bubble sort. If you just write IDEs help find errors, that generic answer gets 0 marks. Always anchor your answer to the prompt-specific scenario.
So how do we guarantee, under the extreme pressure of the exam clock, that we never make those 3 mistakes? I strongly encourage you to use a memory hack strategy. You need to create your own mnemonic, using the first letters of key IDE terms to lock in your retention. For example, to remember the core benefits of an IDE, you could use the acronym SAFE, S-A-F-E. That stands for syntax highlighting, autocomplete, formatting, and error diagnostics. Whenever you flip the page and see a question about IDE features, before you even read the full prompt, you immediately write SAFE in the margins of your paper. This does something incredible to your brain. It instantly structures your thought process. It grounds your algorithmic thinking. It lowers your anxiety. And most importantly, it ensures you hit every single major point on the examiner's rubric without panicking. It's such a simple cognitive backdoor, but it is incredibly, undeniably effective. It's literally a cheat code for your memory.
Mastering the Peel framework, systematically deconstructing algorithms, avoiding those 3 fatal mistakes, and deploying memory hacks fundamentally changes the way you approach this entire paper. It takes you from hoping for a good grade to systematically engineering one. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly explainers. So, here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @theexams_IGCSE and click that bell. Don't let another exam pass you by without having the best strategies in your arsenal.
Now, it is time for you to actually put this into practice. I challenge you to apply the deconstruct, solve, evaluate method to your very next past paper. Actively hunt for those method marks, write down your working out, and structure your thoughts logically using the Peel framework. But as you're doing that, I want you to ask yourself a bigger question. If integrated development environments and AI become so incredibly advanced that they can write, evaluate, and fix our logic automatically, will the true skill of the future computer scientist be writing the code itself, or will it simply be knowing the right questions to ask the machine? Think about that. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this explainer with a study partner. Ace the Exams. Your Cambridge success starts here. Keep analyzing, keep deconstructing, and we'll see you in the next explainer.